Hi, it's Mr. Anderson and welcome to Biology Essential number 42. This is on the Hardy-Weinberg equation and its real-life applications. It is named after G.H. Hardy and Wilhelm Weinberg, the two people who provided the equation's mathematical proof. And what these two proved was that given a certain number of conditions which are satisfied, we can calculate the allele frequency in a population, which also allows us to calculate the genotype frequency. So, in this podcast, I'll be going over what the Hardy-Weinberg equation actually is. I'll also go over the conditions that need to be satisfied for this equation to work, and we'll also have some practice problems, and I'll show you how to work those out. And we'll finish with how you can use this equation in real life. Okay, so let's start with the equation itself. As I previously mentioned, the equation enables us to calculate the frequency of dominant and recessive alleles. Now, what does that really mean? Well, if we know the allele frequency, it allows us to predict the expected genotypes in a population. And so, we measure the frequency using P and Q. P will represent the dominant allele, and Q will represent the recessive allele. And if you don't know what dominant and recessive alleles are, you may want to watch the previous video on Mendelian genetics. But you will also notice that I have two equations on the screen. And why is that? Well, that's because the first equation only tells us about the expression of alleles in a population, which doesn't tell us the specific genotypic ratios, such as homozygous dominant, homozygous recessive, or heterozygous. So if we really want to find out the little details, we have to use the second equation. And that equation will be p squared plus 2pq plus q squared, which equals 1. And this might scare you at first, but if we break it down, it's really not that bad. So we already know that p is the frequency of the dominant allele and q is the frequency of the recessive allele. And you will notice that we already have p and q from the previous equation. And so all we need to do is plug in the values for p and q into our second equation. So, for example, to find the frequency of the homozygous dominant allele, all we need to do is simply square the value of p. And similarly, we can find the frequency of the homozygous recessive allele by squaring the value of q. So those are the easier parts. Now what about the heterozygous frequency? Well, that works just the same way as the other frequencies, where we just plug in the values of p and q. So we would multiply the values of p and q by itself and then double it. And all of that has to equal 1. And later on, I'll show you how you can work backwards and find the values for p and q from the second equation. Okay, however, in order for all of this to work, in order for there to be what we call Hardy-Weinberg equilibrium, there are certain conditions, in fact 5 conditions, which have to be met. First of all, there must be a large population size. And we want a large population size so that we don't get any variation in the gene frequency just by chance. Second, there must be random mating, which means that individuals in the population do not choose their mate, and this actually occurs frequently in nature. Third, there can't be natural selection because we want the genes to be equally distributed for our equation. Basically, we don't want any genes to be selected for or against in our population. Fourth, there must be no gene flow, meaning that there cannot be a transfer of different genes from another population into our population. Lastly, we don't want any mutations to occur in our population. So, when these conditions are met, we can finally use the Hardy-Weinberg equation. What all of this really means is that the population cannot change in order for the equation to be accurate. But realistically speaking, natural populations are always changing because they are constantly under the influence of some evolutionary force such as mutations or natural selection. Now you may be thinking, well, what if the conditions are impossible to meet? Why would we even bother learning these equations? Well, from the information we already know, we can use this equation if A, we assume that a population meets all of the conditions for a Hardy-Weinberg equation, or B, we know the frequency of all the genotypes in a population. So if we already know what q squared, 2pq, and q squared are, then we can see how far the population has deviated from the predicted frequencies. It'll also probably help you in your high school biology class. Okay. So let's move on to some practice problems, and let me pull these problems up and If you want to work on these problems on your own first, feel free to pause the video at this point, and then you could come back and start the video again. Alright, so let's go through these. Question 1. 32% of people have hitchhiker's thumb. Given this, what percent of humans are heterozygous for hitchhiker's thumb? So let's break down the information in the question. Well, they're telling us a number here, and that number is the percentage of people with hitchhiker's thumb. And hitchhiker's thumb happens to be a recessive trait. So we already know that Q will be equal to 32% or 0.32. Now that we know Q, what is the probability of P, or people who don't have hitchhiker's thumb? Well, we simply just use the equation here. So if we substitute 0.32 for Q, then P has to equal 0.68 in order to equal 1. But we still don't know the percentage of people who are heterozygous for hitchhiker's thumb. In order to find that, we have to use a second equation. So let me get a different color here, and we'll go with this color. Luckily for us, we have already done most of the work. We have already figured out what P and Q was from the last equation, so all we have to do is substitute it in to 2PQ, which again is used to find the heterozygous frequency. So we just do 2 times 0.68 times 0.32, which gets us, let me get out a calculator, which will get us 0.4352 or 43.52%. So this means that the population, or 42.53% of people in the population, are heterozygous for hitchhiker's thumb. Okay, so let's take a look at the next one. The next problem actually gives us a table, so let's look at that here. So it says that there are 160 people who are homozygous dominant for unattached earlobes, and there are 480 people who are heterozygous for unattached earlobes. And lastly, it says that 360 people are recessive for unattached earlobes, which means their earlobes are actually attached. So in total here, there are 1,000 people in this population. So what is the question asking? Well, it's asking us to find the frequencies of the unattached and attached earlobes. In other words, it's asking us to find P and Q. So let's repeat this, repeat the same procedure we went through for the last problem. We already know that 160 people out of 1,000 people are homozygous dominant for unattached earlobes. So what would that be? Well, that would be our P squared right here. So 160 out of 1,000 will be 0.16, And so everything else is just the same. So for 2PQ, which would be our people who are heterozygous for unattached, it says that 480 people out of 1,000 are heterozygous. So 2PQ will be 480 out of 1,000, or 0.48. And these people will also be carriers for the unattached earlobe trait. And P squared will be our people who are recessive for unattached earlobe. And so we see that 360 people out of 1,000 people are recessive for unattached earlobe. So our P squared will be 360 out of 1,000, or 0.36. But we still don't know what P and Q are. So how do we find that? Well, we need to realize that our values for P squared and Q squared are our values for the homozygous dominant and recessive alleles. So those are the values of P and Q, but just squared. So all we need to do is just work backwards from here. So let's find P first. We found that P squared is equal to 0.16. So how do we find P? Well, all we have to do is just square root the value of P squared, or in this case, 0.16. And so, if we take the square root of 0.16, we find that P is equal to 0.4. And for Q, we can actually solve this two ways. One way is you can take the square root of Q squared, or take the square root of 0.36 in our case. The easier way, however, is to just subtract 0.4 from 1 minus 0.4, and that will get us a Q value of 0.6. So this means that in our population gene pool, the frequency of the allele for unattached earlobes is 0.4, and the frequency of the allele for attached earlobe is 0.6. Okay, and so when would we ever use all of this? When would we use this equation in real life? Well, it's primarily used for evolution. So what I have here is a graph of the Hardy-Weinberg equation, and you can see that on the top we have the frequencies of the dominant and recessive alleles, or P and Q. And on the left, we have the frequencies of P squared, 2PQ, and Q squared. And this is what the frequencies of a certain genotype will look like if the population meets the Hardy-Weinberg equation. But like I said earlier, a population will never be at Hardy-Weinberg because populations are always evolving. And so, what's the point of this? Well, it gives us a baseline of what the genotype would look like if the population were not evolving. So, for example, a homozygous dominant gene will become more frequent when a homozygous recessive gene goes down in a population at Hardy-Weinberg equilibrium. So, scientists will actually find a population, record the frequencies of a certain allele in that population, then compare it with the Hardy-Weinberg equation tells them. In other words, they will see how much the population deviated from the Hardy-Weinberg equation. And from there, the scientists can predict what condition got violated and caused the frequencies to change. So this is Hardy-Weinberg and how to solve basic problems, and so I hope that's helpful.